All right, so this is part 2 of the video, topic 4.4 from the IB Chem Guide. If you haven't already watched video 1, make sure to do that before you get here. So here we're talking about intermolecular forces. So, and you're going to have to really listen for the inflection of my voice, but so far in chemistry, you have mostly talked about intramolecular forces, which are chemical bonds. They're what hold molecules together, or ionic compounds together. However, we also want to consider intermolecular forces, which are what hold discrete molecules together in most of the applications that we're going to be looking at today. Okay, and the strength of intermolecular forces dictates the physical properties of a substance. So we're going to look at examples related to melting and boiling points. We'll also talk about things like volatility and solubility as examples of physical properties that are directly related to intermolecular forces, both the types of those forces and the strength of the forces. So the first type of force we're going to look at are London dispersion forces. And these are, if you remember back from the Chem Guide, these are the weakest type of intermolecular forces. And the way they work is you have two molecules, so that's what in row 1 of our picture here, you have two molecules that these are meant to be perfectly symmetrical, non-polar, diatomic molecules, okay? But the electrons that are in those molecules, rather than thinking of them as sort of little points of charge in shells, the way we've always thought of them before, it can be helpful to think of the electrons as existing in sort of a cloud, okay? And sort of a cloud that can move around. And what happens to that cloud is sometimes it shifts in such a way that you create a region of electron density on one side of the molecule, or a region of high electron density on one side of the molecule, and then a region of low electron density on the other molecule. That's called an instantaneous dipole, okay? It's not because the molecule is polar, it's just because the electrons every once in a while are going to shift in such a way that you create a dipole, an instantaneous dipole. And now, if there's another molecule near that instantaneous dipole can induce a dipole on that adjacent molecule, because if we think of the red here as being the positive part of this dipole, it's going to pull on the electrons in the adjacent molecule. It's going to be attracted to those, so it's going to pull that electron density over to this side, inducing this dipole that we see here. And then those two molecules are attracted to each other. Before, there wasn't really any attraction, but now, with this instantaneous dipole and the induced dipole, there's an attraction, so those molecules want to stick together. Now, if we think of the details of this, obviously, well, maybe not obviously, but larger molecules are going to have way more electrons that can shift around in that cloud, which means that there are way more places on the molecule for instantaneous dipoles to happen. So when we look at London forces, actually one of the biggest factors that contributes to the strength of the London force is how many of electrons are in the molecule. Okay, and that can result both from having just really big molecules. For example, like the molecules that make up oil, obviously make oil liquid, whereas you have similar molecules with similar types of bonds, but they're much smaller. Something like propane is not a liquid at room temperature. Okay. The other thing, though, is we can just look at the size of the atoms. If you have really big atoms, something like an iodine in a molecule, then that's going to mean that you have stronger London forces than if you had a smaller halogen like chlorine or fluorine in that same molecule. Okay, so larger molecules, both in terms of the number of atoms in the molecule or in the size of those atoms, will have stronger London forces. Okay, next type of intermolecular force is a dipole-dipole force, and this is the type of force that holds polar molecules together. Although we're going to look at another example next, but in general, polar molecules have dipoles, if you have two adjacent polar molecules, like these hydrogen chloride molecules that you're showing right here, then the dipoles can line up in such a way that you have electrostatic attraction. So here we have the negative pole on this HCl attracted to the positive pole on this HCl. Okay, and then those dipole-dipole forces will cause an attraction, so that's an intermolecular force. Okay, and if you have more opportunities for dipole-dipole interactions, you're going to have stronger intermolecular forces. Pretty straightforward. This is another example. It's not one that IB asks you to know, but it is a good one to consider because we often talk about how ionic compounds are soluble in water, and you haven't necessarily had a lot of depth in that. So what we're looking at here are water molecules, which have a permanent dipole, right? Because the oxygen is negative and the hydrogens are positive. And what you're seeing here are the dipoles on those water molecules, the negative part of the dipole, being attracted to a positive sodium ion. Okay, so because we're still talking about positive and negative charges, even though this is a neutral molecule and this is an ion, we can still have those electrostatic interactions. So there's dipole-dipole interactions, like you're seeing here, but you can also have the ion interact with the appropriate end of the dipole. Okay, so you can have ion-dipole interactions as well. Okay, and then the big one, hydrogen bonding. This is the strongest intermolecular force that we look at. And it's actually sort of a specific case of dipole-dipole interactions. So this is when you have a hydrogen bonded to a very electronegative element. Specifically, it has to be one of these three: fluorine, nitrogen, or oxygen. And this creates a particularly strong dipole because that hydrogen, it has relatively low electronegativity. It's also basically just a proton, right? A hydrogen has just one proton in its nucleus, and if it's sharing its electron with a highly electronegative element, then it's kind of just a proton hanging off the side of a molecule. So it's a very strong center of positive charge, and then the electronegative element, if it's a very electronegative element it's bonded to, then that's going to be a pretty strong, there's going to be high electron density around that highly electronegative element or atom. Okay, so hydrogen bonding is just a really strong dipole-dipole interactions, okay? And we're seeing the dipole-dipole interactions of water right here. So you can see the hydrogens, which have a slightly positive charge, will line themselves up so they can be attracted to the negative oxygens. And this explains a lot of the physical properties of water, how it's quite dense, it's a liquid at room temperature, and then also things like how ionic compounds are soluble in it, all those things, okay? Hydrogen bonding. Okay, so here I'm just going to go through a few pictures of different intermolecular interactions here. So that's an ion-dipole interaction. We already saw that picture. And then here is a hydrogen bond. So I like this example of a hydrogen bond because it's illustrating how you can have hydrogen bonds between things other than water, because water is such a classic example we always look at. But here we have an example of an organic compound. So methanol is an example of an alcohol. And you'll notice that we've got this oxygen here that's bonded to a hydrogen. So the hydrogen is slightly positive and it's going to be attracted to the slightly negative part of the water molecule. Alcohols are miscible with water, generally speaking, because of these interactions between the hydroxyl groups and water molecules. Okay, and then here's an example of a dipole-dipole interaction. So we've got chloroform, which is, obviously it's tricky to see, but there's a carbon in the middle here, and then we've got 3 chlorines plus a hydrogen. So the hydrogen has a slightly positive charge, and it's attracted to the slightly negative charge on the oxygen right here. Okay. Then we have what's called an ion-induced dipole. So this is getting a little beyond the content you need to know, but here we've got a relatively large but non-polar molecule, and if it's near an ion, then the the charge of the ion is going to sort of induce movement in the electron clouds that are around this hexane. It's going to cause those electron clouds to move around and induce a dipole. Okay, so if you have a negative ion over here, I'm sure you can imagine that that's going to repel the electron cloud to the other side. So you're going to have a slightly positive part of your induced dipole over here and the slightly negative part on the opposite side from the ion. And obviously that would be reversed if we had a positive ion here. Then the electrons would be attracted to that, and you would have the induced dipole in the opposite direction. Okay. The same thing could happen, maybe the effect would be a little bit smaller, but the same thing can happen if you have a polar molecule adjacent to a non-polar molecule. You can induce a dipole in the same way. So here, negative pole on the acetone molecule, because the oxygen is going to be slightly negative. It's going to repel the electrons in the hexane, pushing them over to the other side. So you've got your slightly positive dipole over here, slightly negative over here. Okay, and then this is an illustration of those dispersion forces. So you can see we've got a relatively large molecule here, octane. The electrons are sort of moving around in a cloud, and every once in a while you're going to have an instantaneous dipole form like that. And then when that dipole forms, it can induce a dipole on the adjacent molecule. Okay, so that picture is supposed to illustrate that. All right, so one more thing to do is to take a look at the graph page, the handout you were given. And this graph, you'll notice along the horizontal axis you have periods, so 2, 3, 4, and 5, and then along the vertical axis you have boiling points, and each point on that graph represents a hydride, so a compound with hydrogen of the element in that element in that period. Okay, and then they're organized. Hopefully you can notice that they're organized by group, and there's a legend on the side that gives you that organization. Okay, so I want you to spend some time sort of looking at the graph and trying to pull out the trends that you see in the graph, and then explaining those using your understanding of intermolecular forces. Okay, so the first part of that task is to look at the graph and label each molecule. Label each point with the molecule it's associated with. And I am going to show you an example of that in a second. Once you've got all your points labeled with the molecular formula, I want you to look at the points that correspond to molecules from the period 3 to 5 elements. I want you to explain the trend in boiling points that you see there. And then I want you to look at the period 2 elements separately, or period 2 molecules separately. Okay, so here is the graph, okay? And just what I mean by the label, so if I look right here, this point right here is in period 2, okay? And if I look over at my legend, that's group 16. So I think, okay, what element is in group 16 but in period 2? And the answer is oxygen. And then I'm just going to fill up any bonding spots on oxygen with hydrogens, okay, because it's the hydride of that element. So this is water, okay? And then if I follow that over, this next one, so period 3, still in group 16, that's sulfur. So hydrogen sulfide is that molecule, okay? So hopefully you get that. I'll show you the other group 16 ones because those are filled in. And then I want you to pause the video, take some time, label each of the other points on your graph with these same sort of molecular formulas. Okay? So pause it. Okay, welcome back. So then the next thing I want you to do, you're going to look separately at the periods 3 to 5 molecules, or 3 to 5 hydrides. So take a look at what we're seeing here and see if you can use the content that was discussed in the previous 2 videos to figure out why we see the trend in boiling points that's happening here. And you don't need to get into the super nitty-gritty why certain ones are a little bit higher than others, but just in general, what trend do you see here, and can you use intermolecular forces to explain it? Okay, so pause the video, take a look at that. Okay, so now that you've explained the trend from the periods 3 to 5 elements, why do things change so much in period 2? What else is going on there? So take a little bit of time, explain that, and then hopefully we'll have some time to discuss this in Wednesday's class. Enjoy. Thanks for watching.